The James Webb Space Telescope has just captured something truly extraordinary. What appears to be the final moments of the star Betelgeuse. After months of careful and silent observation, Webb recorded the beginning of the star's collapse, a moment that scientists have long theorized about, but never seen in real time. Betelgeuse, a red supergiant located just 642 light-years from Earth, is now in the midst of a spectacular explosion. Unlike past detections of distant supernovae, this is happening in our cosmic neighborhood, and we're watching it unfold live. What Webb saw was nothing short of revolutionary. Massive shockwaves are tearing through the outer layers of the star, and jets of plasma are shooting into space. The gravitational impact is so intense it may be distorting the fabric of space-time itself. For the first time, instruments are providing direct, unfiltered data, not theoretical models of a star imploding. Webb has mapped enormous convective bubbles erupting from Betelgeuse's surface, traced plumes of hot gas dispersing into space, and detected energy signatures from a collapse so violent that it's forcing scientists to rethink what we know about supernova mechanics. Betelgeuse, one of the brightest and most recognizable stars in Orion, has always intrigued astronomers. But now it's more than a red giant. It's a real-time case study of stellar death. Webb has detected rare elements like technetium and yttrium forming inside the explosion, materials that are only synthesized during the final breaths of massive stars. These elements are more than mere curiosities on a periodic table. They're part of the very matter that makes up planets, life, and even our own bodies. This explosion isn't just a light show. It's the same process that once seeded Earth itself. Webb's data also suggests that the universe doesn't simply burn out. It recycles. As Betelgeuse sheds its layers, a halo of dust and gas is forming around it. Webb's instruments reveal that hot waves of gas are disturbing nearby interstellar clouds, changing the very chemistry of space around them. There's even the possibility that gravitational waves were released during the collapse, ripples in space-time itself. If confirmed, this would mark the first time humanity has directly linked a visible supernova to a measurable gravitational event. But there's an even stranger twist. Betelgeuse's core isn't collapsing symmetrically. Webb has picked up signs of fallback, where some ejected material is being pulled back inward. Magnetic fields are creating chaotic voids and irregular plasma patterns. Some astrophysicists believe we might be witnessing the creation of a transitional object, possibly something between a neutron star and a black hole. Though this idea remains controversial, Webb's data makes it a possibility we can no longer ignore. People naturally wonder, are we in danger? Thankfully, the answer is no. Betelgeuse is far enough from Earth that its radiation won't harm us. However, its explosion could still influence our corner of the galaxy. Gamma rays, optical fluctuations and high-energy particles might affect the behavior of nearby gas clouds or subtly alter how starlight reaches us. Webb is monitoring every wavefront, measuring its speed and intensity, giving scientists a front-row seat to one of the universe's most powerful processes. This event is providing invaluable data about how stars evolve, how galaxies form, and how the elements essential to life are forged. It's one thing to theorize and quite another to observe it in real time. We now have a direct view of how a star's death can spark new beginnings. As Betelgeuse vanishes from Orion's shoulder, it's being replaced by an expanding nebula, colorful cloud of debris and energy, marking the spot where a cosmic giant once lived. Webb's observations prove that stellar endings are not final. They're transformations. The death of Betelgeuse is creating the building blocks for future stars, planets, and perhaps even life itself. In the remnants of this massive explosion, Webb has found traces of rare materials like aluminum-26 and iron-60, radioactive isotopes that decay over millions of years. These same isotopes are found in meteorites on Earth and were long believed to originate from a nearby supernova. Now we're watching that process as it happens, confirming a theory that explains how our own solar system may have formed. Even more unexpectedly, Webb's instruments picked up unusual concentrations of phosphorus, one of the key elements needed to form DNA. This early appearance in the ejected material suggests that the ingredients for life may form faster and more frequently in the galaxy than previously believed. If every supernova is capable of seeding space with the raw materials for life, then our universe may be far more biologically fertile than we ever imagined. Following the explosion, ground-based telescopes noticed a dramatic increase in optical and ultraviolet emissions from Betelgeuse, but it wasn't just brighter light, it was structured. The shockwave collided with older layers of material the star had shed, creating a series of concentric rings. These rings are like time capsules, preserving the history of the star's life before it died. Each layer reveals information about mass loss, instability, and deep eruptions. It's a detailed autopsy of a star, unfolding in real time. Then, something even more unusual occurred. Radio telescopes in Chile and South Africa picked up structured, low-frequency signals coming from the area. These weren't alien messages, but likely bursts caused by magnetic field interactions or shockwave collisions. Such signals are usually associated with magnetars, hypermagnetic neutron stars, which raises the tantalizing possibility that Betelgeuse might be transforming into one. Observatories like LIGO and Virgo have detected gravitational waves with a lopsided rhythm, suggesting the core remnant isn't a neat, spherical object. If Betelgeuse has become a magnetar or something, even stranger, it would be the closest example of such an object ever studied. Webb hasn't just looked at the core. It's studying how Betelgeuse's explosion is transforming the space around it. Previously, calm dust clouds in Orion are shifting. Some are being ionized, while others are pulled into motion by radiation pressure. The Atacama Large Millimeter Array, ALMA, has even confirmed that new star-forming clumps are emerging just outside the debris field. The star's death is literally giving birth to new stars, and Webb is capturing it down to the molecular level. Even the Hubble Space Telescope, while less advanced than Webb, has contributed by tracking the shockwave in ultraviolet light. These observations are helping scientists build 3D models of the explosion and understand how different elements of light interact with the expanding cloud. Soon, Webb will narrow its focus further, turning its instruments toward the core in an attempt to determine what exactly has formed, whether it's a neutron star, a black hole, or something entirely new. What makes this event especially meaningful is its connection to human history and culture. Betelgeuse has been a familiar presence in the night sky for millennia. From the myths of ancient Egypt to the navigators of the Pacific, it's been a point of reference, a celestial constant. Now, that beacon is fading. Future generations may never see Betelgeuse the way we did. Instead, they'll see a nebula, a reminder that even the most massive stars must one day transform. In the final days of Betelgeuse, Webb has given us more than just scientific data. It has given us perspective. This event is a mirror reflecting the impermanence of all things and the remarkable ability of the universe to renew itself. From the dust of a dying star, new worlds may one day rise. Every atom in our bodies was born from a similar collapse, some ancient supernova's final scream into the void. But the story isn't over. New data from Webb shows subtle flickering pulses at the center of the expanding cloud, possible signs of a newborn neutron star. If confirmed, these pulses would mark the formation of one of the most extreme objects in existence. A neutron star is so dense that it squeezes the mass of our sun into a sphere just a few kilometers wide, and it spins rapidly, emitting radiation in predictable pulses like a cosmic lighthouse. That may be what Webb has found, the birth of the nearest pulsar ever witnessed. Radio observatories around the globe have joined in, scanning for signs of repeating pulses to confirm the object's identity. Meanwhile, Webb's infrared instruments detected a fast-spinning torus, a ring of gas circling the core. This wasn't expected, especially not this early. It suggests that the star collapsed asymmetrically, flinging material outward in a flat equatorial direction. This is one of the signatures astronomers associate with stars that may eventually become black holes, depending on their mass and spin. Webb is still searching for signs that a black hole might be forming. If one exists, it may be hidden behind dense dust, feeding on leftover material and generating faint X-ray emissions. Future missions like NASA's upcoming Lynx Observatory could help solve that mystery. Meanwhile, Webb continues to find new molecules in the cooling debris, carbon chains, sulfur compounds, and silicon-based clusters, the same molecules involved in planet formation. This rapid chemical assembly was once thought to take centuries. Instead, it's unfolding in mere months. The speed of this transformation suggests that the birth of habitable worlds might happen far faster than previously believed. It's a profound reminder that destruction in the cosmos often marks the beginning of something new.